How do we indicate algebraic symbol represents a vector quantity? Remember in the lesson we talked about putting an arrow over top of whatever our vector is. So if our vector is b, yeah, sure. Or if it's f, or if it's lambda, having that arrow over top tells us that it's a vector and we need to treat it as such. Explain what components of a vector are. Components of a vector are the pieces of a vector, the x piece and the y piece. And when you add those two pieces together through Pythagorean theorem, that will give you the complete resultant vector, or the total vector. Draw the components on the right and state the components. So my left, we're going left and up. We're going left 1, 2, 3, 4. Then we are going up 1, 2. So x is -4 because we're going left. We're assuming right to be positive and left to be negative, and up to be positive and down to be negative. Left 4 and then up 2. There we go. Explain the process of adding vectors graphically. I'm going to stick with the tip to tail because, again, that is just more universally accepted. It's just easier for every single problem. You're not limited to the constraint of only using 2 vectors. Tip to tail. We're going to have vector A, and then we'll have vector B. And let's say we want to add them together, and we're going to end up with a green vector. What I can do is I can take vector B, and I can move it, as long as I don't change the angle, right there. And now my resultant, back to the pen. My resultant is this. Using that lasso tool in OneNote is really pretty cool for this. How do you add vectors by components? Add components. It's not really that simple. First, we have to resolve the vector into components. Then we can add the components. Remember I hat, J hat, K hat for AP Physics C, or XY for AP Physics 1. How do you find the components of a vector? In the x direction, we're going to do the magnitude of our total vector times cosine of the angle that the original vector is at. And in the y direction, we're going to do the magnitude times sine. Or not times, sine theta. Yeah, magnitude times theta. Magnitude times sine theta. There it is. This is going to get a little bit more complicated, of course, when we throw in an extra angle in there. An example of that is whenever we have something on a ramp. There's a different way that we have to handle that because there is no obvious x and no obvious y. So keep that in mind when you have this formula. As an example, if we have an initial velocity, which I'm going to use that subscript 0, it's really subscript naught, N-A-U-G-H-T. So V naught represents my initial velocity. If I have an initial velocity, this vector at this angle, then my x component is going to be the magnitude of the total vector, which is V naught, times cosine, because we are adjacent here, cosine of that angle. And then for my vertical component, it's going to be the magnitude of my total vector times sine because it's opposite. How can you change a vector's components into the magnitude and direction? Pythagorean theorem. Is how we can get magnitude. To get the direction, we can use trig. And we actually have this kind of shortcut, if you want. We derived it in the lesson, but I'm just going to jump to it. Arctan y component over x component will give us our angle. Remember, if you have a negative angle, watch out. In the examples below, vectors shown on the top grid using the parallelogram, draw the vectors. Parallelogram. It's okay. I mean, it's pretty easy. And our resultant, let me make this a bit. There's a resultant. Remember, to draw the resultant vector, we're going to start from the same spot. We're just drawing parallelograms, and then where do they meet? That's it. Using the tip-to-tail method, show how these vectors can be added. And then draw the resultant. So vector A goes up 3 and to the right 2. Vector B goes up 1 and left 1, 2, 3, 4. Making my resultant that. Vector A goes down 2 and to the right 4. Vector B goes down 3 and to the right 1. Resultant. Hey, you guys don't have to watch every second of this fascinating bit of YouTube here. You can skip forward to the answers if you like. I won't tell. Up 1 to the right 3. Next one, 1, 2, down 2 to the right 4. Uh-oh. I'm going off the grid. I'm going to try a different vector. So I'm going to hold off on this one. 1, 2, 3, down 3, left 2, 1, 2, 3, 1, 2. Okay. And then this one, 1, 2, 3, 4, 5, 1, 2, 3, 4. Gonna go left 5, up 4. 1, 2, 3, 4, 5, 1, 2, 3, 4. Now this one we go down 2 and to the right 1, 2, 3, 4. Down 2 and to the right 1, 2, 3, 4. Wait a second. They just connect. There is zero resultant here. That's okay. If this represented a force, when we looked at 4 different forces acting, then we would say there is no net force acting. If this represented displacement, then we would say there is no displacement. You'll hear plenty more about those things soon in class. Vector A is magnitude 5, B is 15. Students know the directions of A and B, but you don't. The 5 students attempt to find the resultant. C equals A plus B. Students then report that the magnitude of the resultant vector C. Andy says the magnitude is 5. Bernard says the magnitude's 10. Cliff says the magnitude's 15. Daniel says 20, and Edward says 25. Which two students are idiots? Oh, that's not nice. Don't call people idiots. Again, not made by me. Okay. We're just going to have to go through it and see what's possible and what's not. So if we have 5 and 15, we could have a positive 5 and a negative 15, and that would lead to a negative 10, and the magnitude is absolute value. Magnitude is absolute value. So then, Bernard, you're looking good. Let's say we have a positive 15 and a negative 5. Oh, wait, that's just going to give me 10. Let's say a positive 15 and a positive 5. That's going to give me 20. Who's got 20? Magnitude 20. Daniel, thank you. Then let's say we have a positive 5 and we did negative 15. We did positive 15. Positive 15, positive 5. Positive 5, negative 15. Let's do negative 5. Negative 15. That's still going to just give me 20. What about 5 and then 15? So 5 squared and 15 squared. That. Let me calculate that. When we do that, we get a magnitude of about 15. So Cliff, you're good. So Edward, you are wrong, and Andy, you are wrong. Of course, if you didn't need to go through all that, you could have seen that 5 and 15 are never going to combine to 25, and 5 and 15 are never going to combine to 5 right from the beginning, but I wanted to go through it so that way you could see all of the stuff. A and B are shown below, show the resultant of the operations. So A minus B, remember, so we are going to go up 1 and to the right 3. What I was saying is remember that when we are subtracting a vector, we're really adding the opposite. So adding that anti-parallel, which would be like this. This goes down 2 and to the left 2, so B is anti-B is going to go up 2 and to the right 2, making our resultant this vector. For vector B minus A, add the negative, so let's start with B, 2 and 2. A, up 1 to the right 3, so we are going to go down 1 and to the left 3, giving us a resultant of this. Twice B, which just means we're going to double B. So we'll draw a B and then we'll draw another B. Our resultant is going to be these two, which I'll just draw right there. Half of B, negative 1/2 B, just like that. The vector V shown components 40, 30. Each second, the vertical component decreases by 10. Each second, the vertical component decreases by 10. Woo! When is V the shortest? After 3 seconds. Because it's going to be 0. What is V's shortest length? 0. When is V the same length that it was at time t equals 0? Move myself out of the way here. So after 1 second, we're at 20. After 2 seconds, we're at 10. After 3 seconds, we're at 0. And we can just continue flipping. So here we're at negative 10, negative 20, and negative 30. So if this was 0, 0 was 30. This is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Is vector, yes, at 3 seconds. Oh, no. Sorry, I'm answering the wrong question. Is the vector v ever 0? No. The y component is 0, but the x component is not changing. Pretty cool. All right. Vector A is magnitude of 4, B is magnitude 3. Choose the directions of A and B. Choose the directions to show how A and B add. So vector A has a magnitude of 4. Vector B has a magnitude of 3. The total magnitude is 7. Vector A has a magnitude of 4. Vector B has a magnitude of negative. Remember, magnitude means absolute value. So vector B might be a negative 3. Well, it would help if I could count, right? 1, 2, 3, 4. There's my vector A. And then vector B. 1, 2, 3. Forgive the shaky lines. I'm drawing while the screen is upright. So now my total magnitude is whatever's left over. And in this case, it's just this little bit here, which is still pointing to the right. Now a magnitude of 5. Ooh, tricky, right? Unless you remember, physics loves right triangles. So let's make a right triangle. 1, 2, 3, 4. There's my vector A. Vector B. 1, 2, 3. And here we'll know the resultant vector is this. Well, what's the magnitude of that? This is a 3, 4, 5 triangle. So right triangle follows that ratio. Vector A is 5. The magnitude is 5. So remember from the PowerPoint, these rings represent the magnitude. So 5 at 53 degrees. 1, 2, 3, 4, 5. All right, so all the way. There's vector A. Vector B is 5 at negative 143. Okay, find the components of each vector and draw on the grid below. Oh, whoops. To find the components, we're going to... Yeah, let's get the calculators out, right? Why not? To find the x component, remember it's going to be magnitude times cosine of the angle. So for vector A, our magnitude is 5. Cosine, this will give us our x component, 53. Plugging that in the calculator. Let's use the whole thing, 53.13. My component is 3. Do this yourself. Check it. Try it. Are you in degrees or radians? We should be in degrees. For the y direction, it's going to be magnitude times sine of the angle. So 5 sine 53. Which is going to give me 4. Hey, it's that 3, 4, 5 triangle again. Even though we got 3.9931775. I'm going to call it 4. It's okay. You remember the pain that chemistry put you through with sig figs? In AP Physics, we're going to just... Right? All right, vector B, 5. Could this be another 3, 4, 5 triangle? Could it be? Let's see. So 5 cosine of 143 will give me my x component. Oh, that's a negative 143.13. Let's make sure we do that right. So that will give us a negative 4x component and 5 sine negative 143.13. There it is. Another 3, 4, 5. Find the resultant of A and 2B by adding the components and using the grid below. So A was 3 and 4. 2B is going to be negative 8 and negative 6. It's twice the components. So our resultant is going to be 5, negative 5 on the x, and then negative 2. So we have our components. Let's add them together to find our resultant. So negative 5 squared plus negative 2 squared, and the square root of that. Square root. Man, I was using a calculator that is not my normal calculator. It was a TI-36X Pro, which is a great calculator. But when I put in square root of 29, I just got square root 29, and I don't feel like dealing with figuring out how to change that. Okay, and then to find our direction, we're going to do our direction formula, arctan of our y component over our x component. Greek letter theta to represent the angle. Remember to take the arctan, so we're doing second tan in your calculator. Unless you're on this calculator, then it is pressing tan twice really fast.